Now if F net external acting on the system is 0, let us say, then acceleration of center of mass is going to be 0. Now if acceleration of center of mass is 0, that means the velocity of center of mass is going to be a constant. And in this there can be two cases. The first case is when velocity is 0, velocity of center of mass is 0 and is a constant. So what does that mean? That means that the center of mass was not moving initially, and because the velocity always is a constant, it's a 0, the center of mass never moves. So the center of mass was initially at rest and it remains at rest at the same point. So the interpretation of this is center of mass was initially at rest and remains at rest at the same point. And when I say same point, I mean same point in space. So that is also pretty important to know, that we will have an axis system, we will have x, y and z coordinate axes, and there in that coordinate system there will be a point that will be the center of mass, and the coordinates of that point will not change with time. And a second case here is when the velocity of center of mass is non-zero and it is a constant. So in this case, the center of mass will keep on moving with that same velocity forever. It implies center of mass keeps on moving with the same velocity forever. Now you have to keep in mind something. We are only excluding external forces. We are not excluding internal forces. So there might be internal forces. One particle may be exerting forces on another particle, let us say. And when one particle exerts forces on another, say the nth particle is exerting forces on n plus 1th particle, then maybe one of them will slow down, the other will speed up. So the individual particles can have varying velocities. The velocities can vary in magnitude and in direction, but the center of mass, it is the center of mass that will keep on moving with the same velocity forever. Now these two lead us to two very interesting results. So let's deal with the first one. The first result: when the center of mass is at rest at the same place in space, that means position of center of mass does not change. That implies the change in the position of center of mass is 0. Now this expression is a vector expression, will have three components. So what this will mean is that the change in the x coordinate of center of mass is 0, the change in the y coordinate of center of mass is 0, and the change in the z coordinate of center of mass is 0. And let me show you what that means in terms of only the x coordinate, and the results will follow as usual for the y and the z coordinates. So let's take the x axis alone and let us see what happens. So let there be these n particles, and you have these n particles, their masses are m1, m2, m3. So you have masses m1, m2, m3 and m4 etc. up to mn are initially at coordinates x1, x2, x3 and so on up to xn, and due to internal forces, or I'm saying that the net external force is 0, that means that there can be external forces acting on one particle which may not be 0, and the net external force on maybe another particle may not be 0, but when you add up all the external forces on all the particles, they may give you 0. So maybe the first term is non-zero, the second term is non-zero, the third term is 0, it doesn't matter, but there have to be other terms that will go and cancel out these terms somewhere. So individual particles can be under the action of external forces, can be under the action of internal forces, it doesn't matter, so they may keep on freely moving around. So the masses m1, m2, m3 etc. are initially at these places, and due to the forces acting on them, move to say x1 plus delta x1, where delta x1 is a small change in the position of mass m1, and delta x1 can be negative, can be positive, it's immaterial. If delta x1 is greater than 0, then the x coordinate of m1 increases. If delta x1 is less than 0, then the x coordinate of m1 decreases. So they move to x1 plus delta x1, comma x2 plus delta x2, x3 plus delta x3, etc., where delta x1 is the change in x coordinate of m1, and that is it can be negative or positive. So implies can be negative or positive. So now let me find out where was the x coordinate of center of mass initially. So x coordinate of center of mass initially was m1 x1 plus m2 x2 plus m3 x3 plus so on, divided by that summation of mi term, and the x coordinate of the center of mass finally was m1, it will be x1 plus delta x1 now, plus m2, and it will be x2 plus delta x2 now, plus m3, and it will be x3 plus delta x3 now, and so on, and there will be a summation of mi in the denominator as usual. And if the net external force acting is 0, then the change in the x location of the center of mass should also be 0. So x center of mass finally should be equal to x center of mass initially. So the expressions on the right hand side should also be equal. When I equate them, first I will cancel off the denominator, second I will open up these brackets, and the first terms of each of these brackets will go off with the terms on the left hand side. So m1 x1 here will go up with that m1 x1 there, m2 x2 here will go up with that m2 x2 there. So what I finally will end up with is, so therefore m1 delta x1 plus m2 delta x2 plus m3 delta x3 plus so on, and all that should be equal to 0. Now this is a very interesting result. What it says is that if let's say there are only two masses m1 and m2, so what I can do is to get an understanding of what this equation says is this. So for only two masses, m1 delta x1 plus m2 delta x2 is going to be 0. So what that means is, if the first mass has an increase in its x coordinate, then the second mass should have a decrease in its x coordinate. Only then the first term will be plus and the second term will be minus then. And so the masses must move in such a way that they compensate for each other's effects. Further, if m1 is heavy and it moves by a small amount, then if m2 is light, it has to move by a large amount so that these two terms become equal in magnitude. So that's the physical interpretation of this equation, and this equation can be used for y-axis and z-axis also in the same manner. So please keep that in mind. This is important, and so let me also box it, the top equation as well as maybe the bottom one, or I think just the top one. So the thing is, please keep in mind that if there are no external forces along x-axis and the center of mass along x-axis was initially at rest, then it will forever remain at rest, it will be at the same place, and then the shifts in the masses will be such that all these terms will add up to 0. So this is one. But what do I get from the second one? If the velocity of center of mass is non-zero, the center of mass will keep on moving with the same velocity forever, but the particles themselves can experience a change in velocity. So the second one is of the same kind, where what I do now is with the velocities instead of the x coordinates. So if velocity of center of mass is a constant and is not equal to 0, then I can write something like velocity of center of mass initially is equal to velocity of center of mass finally, and this equation can be opened up. I can say this is m1 v1 plus m2 v2 plus so on the left hand side, divided by summation of mi, and on the right hand side that will be m1 v1 plus delta v1, let us say, or maybe instead of saying m1 plus m1 into v1 plus delta v1, where I mean that it's initial velocity plus a change, I can immediately write that as final velocity. So what I'll have to do is use a subscript on the left hand side. So v1 initially and v2 initially, so I'm adding that I subscript, and on the right hand side that will give you m1 v1 v1 finally plus m2 v2 finally plus so on, and all that divided by delta summation of mi. So this expression will then finally give you m1 v1 initially. So for the initial velocity, maybe if I use a variable u, m1 u1 plus m2 u2 plus so on is equal to m1 v1 plus m2 v2 plus so on, which essentially is the law of conservation of linear momentum for a system of n particles which are not under the action of any external force. So please keep in mind that this is the law of conservation of linear momentum. So the linear momentum of a system of n particles will be conserved if the net external force acting on the system of n particles is 0. The linear momentum of a system of n particles will be conserved if the net external force acting on the system of particles is 0.